Okay, so this is Psych 522. It is October 15th. And in today's lecture, it's basically a two-part lecture. We want to talk about shrinkage methods, and then we want to talk about principal components analysis. So remember last time we talked about the bootstrap, we talked about cross-validation methods and things like that. Well, a lot of these things come down to trying to select what is a pretty good model, right? You're trying to select what is the best model, or at least trying to select a model in a particular way that you can maybe assign a degree of importance to predictors. Well, the shrinkage methods allows us to do this to some extent. So they're one approach for potential model selection. Okay, that's the first thing to realize about shrinkage methods, is that they can actually help you arrive at the most suitable model. Now, like with all things, they're not going to be perfect. Okay? They're not going to be perfect, but they could potentially help out a little bit. So let's talk about the idea of what I like to call a candidate predictor. Okay? So when you talk about a candidate predictor, as you may have read in the article that I posted, you have a whole bunch of variables, right? You have a whole bunch of variables in the population of variables. Okay, so these are all just a bunch of variables. Whenever you do modeling, as I think we've talked about already, is you're selecting some variables from that whole population and you're considering them to be candidate predictors. So there's a smaller set, that's a subset, right? This is a subset of this, and these become your candidate predictors. The next step in model building is to try to figure out a way to get those candidate predictors into a final model, okay, into a final model. That's the idea. So you might end up with, maybe 3 or 4 or something like that. Now, the point of the reading that I gave out, in addition to talking about these regularization and shrinkage methods as an overall summary, is that sometimes this idea is overlooked, right? We overlook the idea that we're actually doing, to an extent, variable selection before we get to any kind of final model. So the stage of going from this whole set of variables to a smaller set of candidate predictors, this is really, really important. You could even argue that this is the most important step before you get to this. Because when you're building the final model, it can't go back into here and select predictors. Okay, it cannot go back into the whole population and select predictors. It can only go by what you provided it as options. So when you're doing things like subset collection, or even like a forward or stepwise and stuff like that, you're always starting off with this particular set. And again, that's to be emphasized, because there's a whole bunch of technology that comes about with how to select variables and how to select models. But if you get this step wrong, then this is going to be wrong as well. So what's the key point as we start this again? We say that whatever variables you do select as candidate predictors, make sure that this set is basically a correct set, as correct as you can make it, before you even consider how to build the model. So, you spend, 10 months considering this, and then you build your model after that for the next 10 months type of thing, right? But this is very important to get to that step. So we're going to assume for what we're dealing with now is that this step has been satisfied, that you have candidate predictors, and then you would like to build a model for it, okay? So what do shrinkage methods do? Well, shrinkage methods constrain, or what's also called as regularizes, the coefficient estimates. Okay, what's a coefficient estimate? That's like a partial regression coefficient. Or equivalently, shrinks the coefficient estimates towards 0. Okay, so what does that mean to shrink them towards 0? Now you have to be careful of this, because if you read sometimes in more purely software-oriented texts, you'll see that sometimes regularization methods are presented in such a way that it just says you want to get the coefficient to 0. Okay, they'll just say you want to get the coefficients towards 0. There are reasons for why we'd like it to go towards 0. And it's usually, as I mentioned, to facilitate model selection. Okay, it helps out a great deal with model selection and predictor selection. So the purpose of it isn't just to drive them towards 0. There's a logic behind it. And oftentimes, regularization techniques will be useful when you have things like collinearity and multicollinearity. Okay? So let's look at the logic of how this works. Well, the shrinking the coefficient estimates can significantly reduce the variance. So this is an idea that when you do have things like collinearity, we know that standard errors can be inflated. So if you have, say, x1, x2, x3, and those are relatively collinear predictors, sometimes performing a shrinkage method can help you select of those predictors which one you want in the model. And that helps to reduce the variance. Now there's two types here that we're going to survey, ridge regression and the lasso. We're going to spend a little bit more time on ridge regression because if you get the idea of ridge regression, then the lasso is much more familiar because it's kind of like a derivative of ridge regression. Remember that when you're looking at these things, you're always talking about the variance versus variance trade-off. So here's my infamous plot by now where I connect the dots. So we have to keep these two things in mind, right? Is that this here, right? This here may be very, very specific to a particular set of data. If you fit that to another set of data, maybe the actual curve or dot connection looks like this. So when you try to be too specific, right? When you try to be too specific, well, you're probably experiencing a relatively low amount of bias, but you're going to have a lot of variance in the learning method. You're going to have a lot of variance in the learning method because if I go to the situation number 2, and the data happen to look a little bit different, well, this is completely out of the question. So we're going to be doing this trade-off as we go on and look at some of these things. Okay, and as we go, you'll notice that I'm highlighting, as I usually do. I'm highlighting certain parts. I've underlined certain parts. You can kind of think of that if you like. I'm not a big fan of PowerPoint, but think of as I go through, those are the main points we need to focus on, almost like if I'm pulling it out and putting it into a PowerPoint. But the advantage of doing that in the book is it gives you a little bit more context so you can kind of see where this is being referred to. So ridge regression, what is it? Well, we know that in ordinary least squares regression, ordinary least squares, okay, that's the classical regression. This is the quantity we want to minimize. Okay, so that's no problem. Residual sums of squares, there's your observed. And what's all this? That's your predicted. Okay, so you can like replace that all with y prime if you want for predicted, but that's all your predicted, depending on how many b weights and x variables you have. So this is what we want to minimize. Well, ridge regression is similar, okay, except we're going to estimate the coefficients a little bit differently so that they minimize a slightly different quantity. So what's the quantity that we want to minimize in ridge regression? Well, if you look at it, 6.5 here looks a lot like this up here. Okay, it looks a lot the same thing. But there's a difference. Okay, so the difference is this thing right here. Okay, and this is a penalty. It's called the shrinkage penalty. Now, to understand what the shrinkage penalty is, you have to see how it's being used here. So we have residual sums of squares plus the shrinkage penalty. So notice that we're not only minimizing RSS, residual sums of squares, we have to add a penalty to it. So that this is the extra term that comprises ridge regression in terms of its minimization procedure. So of course, the next question is why are we doing this, right? Why are we doing this? Well, if you look at this explanation here, they're not going to tell you exactly why we're actually adding this penalty, okay? It's not going to make complete sense, and that's why I have I have the pumpkin over here and I have the star over here. We're going to look at this, but this is not going to give us the answer, okay? And you're going to see why as we need a little bit more information a little bit later in the chapter. But for now, let's just look at what we have. Well, we have a tuning parameter. So that's a lambda. Now that's not an eigenvalue. Okay, when we look at principal components analysis in chapter 10, at the second half of the lecture, we're going to be calling these things eigenvalues. This is not an eigenvalue. It's just a symbol. It's just a symbol that's being used to denote a quantity that is greater or equal to 0. So it has to be a positive number, or 0. So tuning parameter plus the sum of the squared weights, okay, plus the sum of the squared weights. So if you look at this particular setup here, you'll see that you're going to get weights from your regression, but you have some control over this tuning parameter. So this tuning parameter is going to be selected separate from the regression. Okay, so it's being selected separate from the regression. You are choosing, okay, you are choosing the value of the tuning parameter, and as we're going to see a little bit later, you're choosing that value and you can run your ridge regression with different values of the tuning parameter. Okay, you can run your regression with different values of the tuning parameter, and then you can select which regression is most optimal. And we'll define how we assess optimality in a second. So again, this whole thing is the shrinkage penalty. This is going to be small, right? The shrinkage penalty is going to be small when your weights are close to 0. And that makes sense because when you look at the sum of the squared weights, if these weights are close to 0, right? If all of these weights are close to 0, well, then you're not adding very much for a given value of the tuning parameter, right? For a given value of the tuning parameter, if the weights are really small, then you're actually not adding very much to residual sums of squares. So you can think of that tuning parameter, you're controlling the penalty to some extent. And we can see that when lambda is equal to 0, the penalty has no effect. And you can see this up here when this is equal to 0, right? When lambda is equal to 0, then 0 times whatever this sum is equal to 0. So under the case that lambda is equal to 0, the penalty has no effect, and ridge regression will produce the least squares estimates. And that makes sense just by looking at the equation. So you set lambda equal to 0, you're getting least squares estimates. You set it to a number greater than 0, you're not getting least squares estimates, you're getting ridge regression estimates. So we can say that as lambda goes towards infinity, in other words, as it gets larger and larger, the impact of the shrinkage penalty grows and the ridge regression coefficient estimates will approach 0. Okay, so as lambda increases and gets larger and larger, eventually your coefficient estimates are approaching 0. Now, again, you may want to ask, why would we want them to go towards 0? Why would you want any of your coefficients to go towards 0? Well, you can imagine that as your coefficients go towards 0, the most practical application of that is it's going to help you in predictor selection, which is what we were talking about up here. It's going to help you in predictor selection. So, one kind of practical offset of this is you're going to be able to hopefully choose a model or a set of predictors that in some sense makes, more logical sense of choosing that as a model. So you can see that ridge regression in this way is a bit of a competitor to best subsets collection, regression, forward regression, and full entry regression. Okay. So this is an important point because we're going to be working with lambda as we go here in a second, and we're going to be changing the value of lambda and seeing what effect it has on some other indicators. So selecting a good value is critical, and you're going to have a different set of coefficients for each value of lambda. So you may ask, well, how many values of lambda should I try out? Well, again, we'll see this in some plots. But that's the basic idea of what we're trying to minimize. But I want to point out here, that in the book, when they write this, when they say the effect of shrinkage, right? The effect of shrinkage right here has the effect of shrinking the estimates towards zero. There's nothing in here that's saying that the coefficients have to go towards zero. Okay, I just want us to pause for that on that for a second. There's nothing in here that says that the coefficients have to go towards zero. So it's kind of worded a little bit weirdly in the book here. So it says the effect of shrinking the estimates towards zero. Well, there's nothing here that you're actually making the coefficients equal zero. You're just selecting a value of lambda. Now, if you set it equal to zero, then yes, this whole term goes to zero. But if you set lambda equal to, say, 2, that's not going to by itself in this equation set this equal to 0, because you have to record your coefficients from what you're getting from the regression. So the point of this is we need to unpack what this does a little bit more rather than just describe it in terms of the residual sums of squares. What we need to really know is we need to understand what is being minimized by what criterion. Okay, what is being minimized by what criterion? And as we're going to see pretty soon, we're going to look at a value S, and that value S is going to be a term that's going to be used in the minimization criteria. Okay, and that value S is going to have a direct implication for what this is over here, for what lambda is. But I just want to point out again that the shrinkage penalty, when we say it has the effect of shrinking the estimates towards 0, well, we're going to adjust the S value, which has an implication for what the lambda value is, but you're also going to get coefficients from your regression. So it's not like this is a completely determined thing where you just play around with this and this will go to 0 right away. And as we're going to see in our plots, when we look at simulation studies of this, I mean, that's going to depend a lot on how powerful are your B's, right? How powerful are your B's? So again, I want to point out that you don't have arbitrary control over, shrinking these right away. There is going to be a shrinkage effect as you change this value, but there's also going to be the effect of your variables, of your B variables. So it's possible that you vary lambda, but some of your B's, I mean, they stick around for a while and they don't go to 0. Okay, they don't go to 0. Now, eventually, as lambda gets larger, we're going to see that they go to 0, but we're going to see in the plots that they can go to 0 at different times. Okay, so that's a key point there. And we'll look at more a little bit what S is pretty soon in terms of the minimization criteria. So there's a lot on this page that they're kind of throwing at you right away that we need to unpack a little bit more. Okay, so do not apply the shrinkage to the intercept. That's what this is about. Do not apply the shrinkage to the intercept. And when you're doing bridge regression, a good idea is to center the X matrix. So there's your matrix of your predictors. You want to center your X matrix to make this work properly. So let's look at this here. We have an example on the credit data. So that's a data set that they've been using in the book for a long time. They have different predictors. They want to predict your credit rating. And here are different predictors. We have income, credit limit, rating, student, etc. So here are 5 predictors. They talk about 10 variables here. There's only 5 predictors in the plot. Okay, so just so you know that of the 10 variables, they're only putting these 5 variables in here. So what are we looking at in this plot? Well, we said that we have this value of lambda, right? We have this value of lambda. We also said that when lambda is equal to 0, you get the least squares estimates, right? When lambda is equal to 0, you get the least squares estimates. So, we have increasing values of lambda going this way. Okay, so lambda is increasing as we go from left to right. So it stands that at lambda equals 0, you get the least squares estimates. So here's the case of how to understand what this plot is telling you in terms of how to understand ridge regression. It's a really powerful plot because look, pretty much lambda equals 0, there you go. There are your estimates, right? Lambda equals 0, this is basically a least squares. So if you want to know, hey, what's my coefficient for income at least squares? Well, it's pretty much darn near over here. How about for student? It's pretty much over here. How about for rating? Over here, over here. Okay, so least squares, you look at it as the starting point here. Now what we're going to do is we are going to perform ridge regression. We are going to perform ridge regression, and we are going to vary the value of lambda, right? We're going to vary the value of lambda. So let's look at the behavior, the complexity in the coefficients, right? The behavior of the coefficients as we vary lambda from a very, very small value, starting with 0, increasingly larger. Increasingly larger. That's what I mean here by the complexity of the coefficients, is there's a whole lot going on as you vary lambda. So watch, lambda goes up, what happens to income? Income almost remains the same up to about here, right? Almost remains the same right about here. Now look, what happens to limit? Limit starts to decrease, and it starts to decrease towards a value of 0. Now, if you think about it, that makes sense that that should start to happen, right? Because we're doing ridge regression, and we just said that ridge regression shrinks coefficients towards 0. So the fact that limit is dropping, even at this level of whatever this one is for lambda, you're getting the decrease here, so it makes good sense. Same thing like student decreases. This one here is starting to decrease because that's a negative number, so a decrease is going up towards 0. It's starting to decrease, but not by very much, but it's starting to decrease. Everything here is going along a decrease, even it's headed towards 0 because it's a negative number. But look at rating, right? Look at rating. Interesting that rating actually increases for a little while and then decreases. So what's this idea here? Well, the idea is what I was emphasizing on the other page, is that even if you adjust lambda, coefficients will behave differently for different variables, and they will behave differently in the company of other variables. Okay, so what I mean there is, if you look at what rating is doing, rating is going up. It's not going towards 0. It's almost like the shrinkage is failing. Now, it's going up. Why is it going up? It's going up because of the complexity of the model, right? It's going up because of the complexity of the model, because these are the candidate predictors. These are the candidate predictors. So in this particular set of predictors, this is the behavior of rating, right? This is the behavior of rating for lambda at this value here. Okay, that's really important because we would think that they would always decrease, but sometimes they increase. Sometimes they increase as lambda gets larger. That's why it's not just a matter of adjusting lambda to get your coefficients to be 0. It's not just a matter of adjusting lambda to get your coefficients to be 0. Otherwise, this lambda, any lambda greater than 0, should result in coefficients that are close to 0, or at minimum, all decreasing. And that's why on the previous page, when they say, you know, if you adjust lambda, it causes the shrinkage. Well, yeah, it causes the shrinkage, but only in the limit, right? In the limit as lambda goes towards infinity. So we see that eventually the coefficient does come down, and we get coefficients equal to 0. And that's what that's saying, because we have the 0 here. So it's equal to 0, but in the limit, I mean, you don't have to go all the way to infinity, right? you can, starts to go to 0 over here, but this is the idea. So again, a really important thing, and looking at other plots in the chapter, you can relate a lot back to what you're seeing here. Now, we'll look at this plot in a second to see what they're up to here, because understanding what this is important. But what I will say right now is that in this plot, we're going to start at the opposite end. So this is going to be our starting point, and then we're going to move this way to interpret it. So what does B hat R stand for? Well, when you look at B stat R, we're seeing very similar information in that right-hand plot, but it's plotting this on the x-axis. Okay, it's plotting this on the x-axis. So the B hat is the vector of the least squares coefficient. So we see it's a ratio, right? There's a lot. I know there's a lot of lines going on, right? There's some like tilted. There's some verticals. Like what's going on? Well, you've got this is division. It's not a conditional probability. It's division. So you see on the bottom we have the B hat. That's the least squares. Now, what does the B with two lines sub 2 mean? Well, that's called the L2 norm. So L, or just L, right? L of a vector, and that's defined as the sum of those squared coefficients. And take the square root. And that measures the distance of B from 0. So we can see that as lambda increases, the L2 norm of the coefficients based on ridge regression, okay, that's what that top number is. The coefficients based on ridge regression, that's what the R is for. As lambda increases, the L2 norm of the coefficients based on ridge regression for a given lambda will always decrease, and so will this value here, okay? So will our ratio. That's the same thing as what we're looking at over here. So what is really going on in this ratio? What do we expect ridge regression to do? We expect ridge regression to lower the coefficients. The coefficients should be headed towards 0. Makes sense then that as we adjust lambda, this number, right, overall, because this is kind of like what the saying is overall, because we're summing all those squared values, this number, numerator, gets smaller relative to the least squares. So you've got numerator, denominator, this goes down relative to the denominator. So if it goes down, then eventually, right, eventually you should start to see things go towards 0. So it ranges from 1, right? It ranges from 1 when lambda equals 0. Well, when is lambda equals 0? That's the case where the ridge regression is the same as the least squares. That's what the book's saying right here. It's the same as the least squares. So that their L2 norms are the same, right? The L2 norms are the same. When lambda is equal to infinity, again, it's unrealistic. You're never going to have lambda equal to infinity, but when you're dealing with these models again, the theory behind it is you have to take it to the limit, right? Take it to the extremes and see what the behavior is. When lambda is equal to infinity, the ridge regression coefficient estimate is a vector of zeros, right? Because as you increase lambda towards infinity, you're eventually going to get, we're not quite sure when all the time you're going to get it, but you're eventually going to get the coefficient vector equal to 0. Okay? In which case the L2 norm is equal to 0. So what we're seeing then, I hope that makes sense. As lambda goes to infinity, eventually your coefficients are going to 0. So when you look at this ratio, we can see that as we adjust, right, as we adjust the lambda, right, we're going to adjust the lambda. I'm going to go back to the plot. All this will make sense when I look at the plot again. When you adjust lambda, well, you're adjusting it relative to what you're getting as the baseline least squares. right? The baseline least squares. Now you're going to adjust lambda and see what happens to the norm for the ridge coefficients. Okay, so let's just go back a little bit and look at the graph. So the way to look at this graph on this right-hand side here, right here, is to start here. Start on this side. When we're over here, we set lambda equal to 0. Now start over here. Apply this fraction to here. What do you get? You get the same ridge coefficients. Okay, so the norm here divided by the norm here is equal to 1, right? It's equal to 1. So we can see that as we head towards this way, right? As we head towards this way to the left, what's happening, right? What's happening is we go from 1 towards 0. Well, the least squares estimates aren't changing because we're not doing least squares. I mean, that's a good reason for why they're not changing, right? Is we're not doing least squares. We're doing ridge regression. So imagine that this denominator is staying the same here, right over here. This is staying the same because this is our starting point. So we got a baseline of least squares. Now we're going to adjust for ridge regression. As lambda increases, what do you expect to happen, right? What do you expect to happen to the coefficient vector for ridge regression? What do you expect to happen? You expect this to get closer and closer towards 0, right? That distance gets closer and closer towards 0. Now, if you look at it, just like we saw in this plot, it's not always like that because look, this one actually goes up, right? That's, which one is that again? That's the rating variable. It actually goes up, but then it starts to go down. So think of this, as the book will say, it's kind of like a fraction of that L2 norm for the least squares regression until you get complete shrinkage over here. Okay. So that's another way of basically viewing the same information as you're looking at this. It only puts it as a fraction of the kind of like that starting point of the least squares. I'm only using the word starting point because if this is a comparison of ridge regression to least squares regression. That's what it's doing, is when you start off with least squares regression, you're over here. Now let's look as we adjust and we see adjust the value of the tuning parameter, we see what happens eventually as we get closer and closer to the limit, right? As it gets larger and larger, what happens? They go to 0, which is why we have a 0 here, where you have complete shrinkage. Now, as you can imagine, allowing it to get larger and larger, I mean, allowing this to grow without bound is not going to be very meaningful, because if in the limit they go to 0, well, you know, you're not going to tell people I let lambda increase towards infinity and wow, I got a vector of zeros, because that's not going to be, you know, very interesting. So we're going to have to select a value here of lambda. You know, maybe we determine that this is the optimal value of lambda, and then those are going to be the values for the coefficients for that model. But important to understand is that as you change the value of lambda, you're going to get different coefficients and get different values. So, you know, long story short, for now, if someone says I did a ridge regression, you have the right to ask, well, for what values of lambda did you try, and what was the behavior that you observed for your coefficients for different values of lambda? And you know, if the article you're reading or the conference you're at or whatever says, well, I just chose one value of lambda, I just chose like 2. Well, then you don't know if that's an optimal 2, or if it was just an arbitrary 2 selected, that'll give you a certain set of coefficients. Now that's unlike least squares regression. That's not like least squares regression, because in least squares regression, we didn't tune anything. We didn't have anything in least squares regression where you can kind of, hey, let's just tweak the tuning parameter and see the behavior of the coefficients. In ridge regression, you have that tuning parameter. So it's going to matter. So if we ask the question right here, let's ask the question, which value of the tuning parameter are you going to want to select? Well, think about it. we're going to want to select some value of the tuning parameter that, as usual, optimizes some function of the data, right? It optimizes some function of the data. So just hold that in your mind right now as to how you're going to select the tuning parameter. Well, it's going to optimize some function. That's the only way to really truly select the tuning parameter. Otherwise, it's completely arbitrary. It's got to optimize. Now, optimize means maximize or maybe minimize, but it's got to do something to give us a rational decision as to what value we're going to choose. So all of this we just talked about up here. Another thing just to mention here quickly is least squares coefficients are called scale equivariant. So if we multiply x by a constant, it rescales the coefficient estimates. Ridge regression can change quite a bit when multiplying a given predictor by a constant. So we have to be aware of that the actual scaling of the predictor variables matters in ridge regression, which is kind of interesting, right? Because we usually don't think of least squares regression as it mattering very much, but in ridge regression, it does matter. So what the book recommends here is that you standardize the predictors. And by their definition of standardize here, they are producing a standard deviation of 1 for each variable by taking the x divided by the standard deviation, but you're not getting a mean of 0 here. So standardizing in this case is not meaning get a mean of 0, it's just getting a standard deviation of 1. Okay. What does ridge regression improve over least squares? So again, returning to our previous question, why would you want to do this in the first place? Well, let's look. As lambda increases, the flexibility of the ridge regression fit decreases, right? Makes sense, because look, as lambda increases, what do we know that the coefficients are going to do? Coefficients are going to go towards 0, right? So the flexibility is decreasing. It leads to decreased variance, but increased bias. Now, why does it lead to increased bias? Remember what bias is. I think the variance idea is pretty clear, but think of the increased bias, right? The increased bias is this idea that, like, if I drew a horizontal line, that this is accounting for the true relationship in my sample. Well, it's probably off. The true relationship in the sample, in the population, is probably more complex than just a horizontal line. So, this has got a lot of bias. This isn't estimating the right thing. That's not estimating the right thing. Maybe the true functional form, here it is again, is maybe something like this. So what does ridge regression do? When we say it has increased bias, it means, you're going to shrink those coefficients towards 0, but, you're going to decrease your variance, but that bias is going to go up a little bit too. So it's a little bit of a trade-off, right? It's a little bit of a trade-off. We don't like bias when we do things, right? If you think about it, almost in anything, we don't like bias, right? Imagine that you're playing darts and you're trying to aim for the target. Well, imagine if I told you, you know what, just allow a little bit of deviation away from that target, and that's going to help other matters. That's going to decrease the variance. Right? So if I told you that, that'll decrease the variance if you can tolerate a little bit of an increase in bias. So the ridge regression estimator is actually allowing you something that we've never ever talked about before and that you've never heard in the stats course, is allowing a little bit more bias, but it's going to help decrease the variance. Okay? And if you think about that again, it makes sense that the shrinking of coefficients is going to accomplish that. Now, on a more practical level, that's this, kind of like the statistical reason as to how it improves over these squares. But on a practical level, what are you hoping? You're hoping that it could actually allow you to select your predictors, right? It could actually allow you to select your predictors, because for a given value of lambda, if I go here, for a given value of lambda, what can we see? Well, we can maybe try to make some sense out of this, that some of the coefficients are going to go to 0 before others. Look, so if I'm going to choose this one right here, this is the value of lambda I'm going to choose. The value, it's not the value of lambda, that's the ratio. But for a given value of lambda, this is what the ratio is. Okay, so it's like if I chose over here, I chose a value of lambda, we're just going to choose this ratio point here of the ridge relative to the least squares. So if you look here, look, you can see that some of the coefficients are above 0, but this one here, which one's that? The income, almost at 0 over here. So that could actually help you in model selection, in predictor selection. And you can say, you know what, this coefficient is doing nothing. This one, the income. These three here are still in the game. They still have values that are different from 0. So you think of ridge regression as a way of shrinking coefficients, not all of them. You definitely don't want to shrink all of them. That would be useless. But maybe shrinking the ones that you can kind of maybe lessen the importance of because they're kind of going towards 0 compared to other coefficients, right? Other coefficients aren't going to 0 just yet. So that's kind of one rationale for why ridge regression will be meaningful. Now, it should be pointed out as well that in the limit, as lambda goes towards infinity, we go to 0. But ridge regression isn't going to push those coefficients directly to 0 for values less than infinity. So we're going to look at another technique in a second. We're going to survey it really quick called the Lasso, which the Lasso regression is a little bit better for making those final model model selections. Ridge regression shrinks them, but it usually doesn't set it to 0 unless you're dealing with very, very large values of lambda. Okay. So there's your advantage. Now, if you look here, we've got the bias, we've got the variance, and we've got the mean squared error in the purple up here. So what happens, again, another simulation study, what happens is you vary the value of lambda. Lambda gets bigger, right? Lambda gets bigger. What happens? Well, let's look for this particular data. We have the bias. Starting at lambda 0, OLS, we have basically an OLS over here, lambda equal to 0. What happens to the squared bias? Well, it goes here, and then it starts to rise. What happens to the variance? The variance starts to drop over here. Remember, they're a trade-off of one another. So it kind of makes sense that you're seeing this type of curve, right? Sacrifice and bias, trade-off of variance, that idea we've been talking about. Well, let's also look at what happens to the test mean squared error, purple, for the ridge regression. Look what happens as you increase the lambda. It drops, but then it also increases over here. So interesting as well that we see the mean squared error. That's the test mean squared error. So that's on a new sample. Gets its lowest point over here. So you can see it's getting its lowest point for a given amount of variance and bias over here. And we can see very much the same effect over here, where again, we have the ratio over here, okay? So a trade-off of the two, but you know, you're usually not trying to minimize one exclusively, right? Like the purpose isn't to minimize variance for whatever you can do, right? You're not going to select a model over here. You're not going to select a value of lambda over here and then, you know, like brag to your friends that you're able to get the variance really low. Right? You're not going to say, look, I got the variance really, really low. Well, then your colleagues are going to say, well, what about your bias? Well, yeah, my bias is pretty high. What about your mean squared? Well, my mean square is really high, but boy, oh boy, like the model I've chosen has, you know, a really, really low variance. You're not going to do that. It's got to be a trade-off, and that's what the point is here. And likewise, you know, selecting a model over here where you have the bias is really, really, you know, low. Well, that's not going to be necessarily, you know, that great because your variance is still high, which results in the mean squared error still being very high. So again, compromise, variance, and bias. Ridge regression tries to allow some bias, right? It tries to allow some bias, but it decreases the variance. So there's a good point of mean squared error being a minimum, which is a nice cross-validation idea to get that mean squared error to a minimum. And we see, for an increase in bias, I'm going to decrease your variance a little bit. That's not a bad deal. That's the idea. If you think about it in terms of a least squares, right? The least squares are unbiased estimators. We're not playing around with bias over here because look, if this is least squares over here, what's your bias? Well, it's close to zero, right? It's close to zero. We're not quite at the 0 point in this graph, but your bias is zero. So if you want to make sure you're not experiencing any bias, use the least squares estimators. The problem is your variance is pretty high, and look at your mean square error. Trade-off idea between bias and variance. Ridge allows some bias. And again, that may sound a little bit surprising that we're actually going to allow bias into our estimator, but that's what ridge regression is doing. And if someone asks you, they say, hey, why are you allowing bias in your estimator? You say, because don't worry, I'm getting something for it, right? That's what you say. You say, I'm getting something for it. You don't want to use a bias estimator if you're not getting anything for it. You're using the bias estimator because it's helping you decrease the variance. It's helping you decrease the variance. That's the purpose of it. Okay, so all of that was pretty much talked about a little bit more. The lasso here is very similar to ridge. Let's just talk about this briefly. There's the penalty. Okay, there's the penalty. Notice that it's going to have a little bit of a different thing here because you're taking absolute value. So there's an absolute value of your weights, right? Absolute value of the weights, but you see the tuning parameters still there. So if you compare this to ridge, you're going to see it's actually very, very similar, but we have a different penalty. So the lasso more technically means we use an L1 norm. There's the L again. Okay. There's the L1 norm penalty instead of an L2. So there's our L1 norm over here. Now, what's the effect of the L1 penalty? Well, the L1 penalty actually has the effect of forcing some of the coefficient estimates to be exactly equal to 0 when the tuning parameter is sufficiently large. Now, remember what we just said about ridge regression. That typically is not the case in ridge regression unless this gets like really, really large, right? Towards infinity, well, in theory, they're going to go to 0. But in the lasso regression, it forces some of the coefficients to be exactly equal to 0 when the tuning parameter is sufficiently large. So when you think of that, coupled with the idea that we just talked about, you say, hey, maybe lasso regression is going to be useful for variable selection, right? If it's going to force some of the coefficients equal to 0, what do we know about coefficients equal to 0? Not interesting, not statistically significant, right? Not interesting. The lasso might help with this because it's going to force them to 0. So it might be useful for model selection or predictor selection rather. Now, having said that, think about that for a second. Do you really care that much if a coefficient is near 0 or exactly equal to 0? Maybe not. Maybe in many contexts, you're fine with doing the ridge, even if you don't get exactly 0. That's still going to aid you in predictor selection. But where lasso comes in handy is lasso forces them to 0, so it kind of clarifies it a little bit more. But I just want to point out that the argument that you have to have the coefficient exactly equal to 0, you don't have to. You can still have it approximately equal to 0, but still perform model selection or predictor selection with ridge. Lasso, the benefit is that you can say it actually performs the variable selection for you because it drives some of those coefficients to 0. So a fancy word here is we say that the lasso yields sparse models. That means it involves only a subset of the variables. Okay, only a subset of the variables. But the same thing as in ridge, the value of lambda is very critical. Okay, so again, I just want to like summarize that point between the ridge and the lasso. The lasso, when we say it produces a sparse model, it involves only a subset of the variables. Now, it involves only a subset of variables. It's not doing that. It's not just selecting a subset and allowing you to figure it out. It's setting some of those coefficients equal to 0. That's how it's selecting the subset. What Lasso is assuming here is that if you have a coefficient equal to 0, that's not interesting, right? That's not interesting. That's what the Lasso is doing. So it's not using only a subset. It's actually setting some of them equal to 0 so that you can actually deduct or deduce a subset from that. Because if one coefficient equals to 0 and the other one equals to 3, you're going to look at these, you're going to say, I'm going to choose this one. Well, all the lasso is doing is setting equal to 0. So, the predictor selection issue is still there, even if you're getting a coefficient equal to 0. It's just that lasso assumes you're just not going to select this coefficient. And usually you wouldn't, but you can also imagine the case where you may want to report a model just to show that you've included the context, right? But usually not. You're just going to go with the B3. Maybe the next one is 5, so you're going to choose the B3 and the B5, and you're going to drop the B equals 0. That's what the lasso is assuming. And that's what they mean by a sparse model. Okay, that's a lot to take in. Why don't we take a quick break, and we'll come back and we will leave off right here, talk a little bit more about the lasso, finish that up relatively quickly. We're almost there. And then we're going to start getting into the principal components analysis right into chapter 10. So take a quick break and we'll be right back.